Okay, guys. Can you guys hear me? Okay, guys. Can you guys hear me? So give me a signal when you guys can hear me, okay? Hey guys, can you guys hear me? You can actually use the group chat to communicate with me, okay? Okay, perfect. Let's give it one more minute while let's give it one more minute while we're receiving more attendance, okay? Here is the first lecture for our new session. So we always have some technical issues here and there. So let's give it maybe one more minute while the students trying to sort out their connection issues. Okay. All right, it's 7:02, so let's get started. Hey guys, welcome to our North American Math Competition basic courses. Today we're going to be focusing on the session 5, functions and advanced functions. For the students who are familiar with our lectures, our lecture is actually classified by different sessions. We have 8 sessions in total. So all the sessions are actually well organized. Try to give you guys the most important concepts for the North American Math Competition. Our lectures covers whatever math competitions from the Canadian exam all the way to the American exam, for our AMC related exams, for our Waterloo related exams. Like the whole point behind this is because all those math competitions, even though they come from different countries, have different targets, but the concepts, they're exactly the same. The technologies, the strategies, how to solve the problem, they're exactly the same. So basically in our lecture, we're trying to give you guys a bit of examples from the Canadian exam, American exam, and some international exams. Try to help you guys, use the technology we introduced in our lecture, try to solve the real problems. All right. So our current session is going to be our session 5. Okay, let's jump to our session 5. Okay. This is going to be our session 5, which is functions and advanced functions. So trust me, function, this is actually a very important concept for the entire algebra. The algebra we can say is actually created or constructed based on the functions. A lot of concepts, a lot of different ways or different strategies can actually find a little bit trace in the functions. So that's the reason we like to use the entire session talking about the functions. Well, functions concept, I gotta say, this is not so unfamiliar. Especially for you guys, you are considered to be a higher grades, you should be able to, get contact with functions pretty much from day one. Think about it from your grade 1, grade 2, you're trying to find some relationship between a bunch of numbers, right? So these kind of relationship can be classified or abstract as a function. So we can say that function is the foundation for our algebra, and most of the concepts is actually elaborated from the function. So when we are talking about function, so maybe we're going to get started with some basic understanding with the function. Something like the basic properties of the function, basic definitions of the function. I think this is exactly where it comes from, right? And we just want to give you guys a quick overview of what we will be talking about for our entire lecture. So at the very beginning, we're going to spend some time talking about the function basics. So we're going to talk about the definition, the domains, the range, like different properties of the function. These are considered to be the foundation of the entire function section. And then moving forward, we're going to talk about some very important properties. Important properties of functions. So namely, we're going to talk about some increasing function, decreasing function. We're going to talk about some even functions, odd functions. We're going to talk about some periodic functions, so on and so forth. So these are actually considered to be the very important and very generic properties for all the functions. We're not really specifying in one specific type of function, but generally speaking, overall, all the functions should have this kind of properties, right? And then we're going to talk about a very important concept in the function, which will be tested from time to time in American and Canadian math competitions, aka that's the maximum value and the minimum value of a function. As long as we have a function, we can have a graph, right? As long as we have a graph, people always tend to see, okay, what is the range of the function? What is the maximum value? What is the minimum value of a function? And taking from there, there will be a lot of interesting properties and interesting strategies. We can basically do a summary and try to share with guys how to determine the maximum and minimum function values. And also bear in mind, these technologies, we are actually introducing all of them during the maximum and minimum value, but they're not necessarily only used for the maximum and minimum value. And these strategies can be transplanted, can be basically transferred into any kind of areas of a function. And you'll be able to see different technologies. We can be used not only for the maximum and minimum, we can basically use it to use a lot of interesting properties of a function. And taking from there, we'll be able to give you guys a little bit of elaboration based on that. All right. And moving forward, we're going to talk about the exponent function and the logarithm function. So these are considered to be a twin brother, right? Because these are actually the inverse operation from exponents all the way to the logarithm. So we're going to introduce some properties and solving strategies for these two functions. And moving forward, we're going to talk about our rational function and fraction function. So these two functions, I think you guys are also very familiar with from day one. So let's try to take this opportunity, sit down together, try to summarize some very important strategies and very important concepts to solve the rational and the fraction related functions. And moving forward, we're going to talk about some Gauss function. Gauss function is a specific kind of function which will be tested from time to time, especially in American exams. If you check all those kind of American exams, not only from the AMC, but AME, even though all the way to go to the USAMO, they're going to be testing this function, like the Gauss function from time to time. Gauss functions definition is fairly understandable, right? You just do x and then this is like the integral, but you can actually find a lot of very important concepts and very important strategies how to deal with the Gauss function. We're going to use a lecture talking about this. And then moving forward, we're going to talk about a very important concept, which is the Theophantin function. Theophantin function is a specific type of function which combines the basic function-related property, the equation, solving the equation strategy, and also number theory. So this is actually a very hot spot. It will be tested in our American and Canadian exams from time to time. So that's the reason we also like to spend some efforts talking about the Theophantin equation or Theophantin functions, the definition, the property, and how to find out the integer solution of a Theophantin function. And this is actually a very important concept, not only for the math competition, from like a higher perspective, Theophantin equations integer function, like the integer solution, is also a very important concept for the entire mathematics. So finding out different strategies, how to solve the Theophantin equation and how to find the integer solution is actually a topic that actually, I would say, in the entire math history for super long time. And different generations of our mathematicians, they're trying to figure out a way, if not a generic solution, how to solve all the Theophantin equations and figuring out their integer solutions. So actually, Amy and they're gonna test it from time to time. So that's the reason we like to take this opportunity and try to give you guys a kind of a summary. Of course, this is going to be a super light summary, right? But at least we're trying to give you guys the idea and different strategies how to solve the problem. All right, this is actually a very short and brief overview what we will be covering for our 10 lectures. Okay, so any questions for me? So far, so good? Just bear in mind, we have our group chat open all the time for the entire lectures. Whenever you have any questions, feel free to post your question into the group chat. So I will be able to see your question and give you the real-time answer, right? So any question, just let me know. We'll be able to help you out right away. Perfect. If all good, let's jump to our first part. This is our first lecture, function basics. Okay, let's jump to a new page for this. Function basics. Like I said, talking about function, this is actually a concept people are so familiar with. This is not the first day we're talking about the functions. So how to define a function? The understanding for functions definition this is actually evolving process. From the very, very beginning, we can have a definition of the function. We always like to talk a primitive definition. This is like a basic definition. Pretty much using our human language, use a lot of common sense, you'll be able to give the definition for function. So what is a function? Function was originally the idealization of how a varying quantity depends on another quantity. Is that right? So this is actually the original definition for function. So what is that? See, we have something. Let's say we have a quantity number 1. They're actually changing. Let's say we can say this is a date, for instance. Okay, so we have January the 1st all the way to December the 31st. So the days, they're changing. So at the same time, each day, it is possible that it's reflecting to temperature, right? Temperature, right? So these days, people already know that, okay, let's say for January the 1st, according to our history, we have so many possible temperatures. But generally speaking, January, you should be expecting a relatively low temperature. So all the way to these days, we're in June, we're expecting a high temperature, right? So this is actually the original definition of a function. We're trying to find out a relationship between two quantities. The first quantity is changing from one value to the other value. And then the other quantity is also changing from one value to the other value. So during this changing process, we somehow can find such a relationship, right? Relationship. So the way people are trying to find out such a relationship is pretty much try to define a function. Is that right? So this relationship can be fairly straightforward or can be very complicated. But anyway, we're just trying to find out a potential relationship, trying to describe this variety from one quantity all the way into another quantity. Right? Like I said, sometimes this relationship is very straightforward. Let's say your age and your height, and your height, excuse me, your age and your height, for instance. Maybe you will be able to find an easy curve. Try to say, okay, most of the students, most of the guys, when they're at a certain age, they will have a specific height, so on and so forth. This is a relatively straightforward relationship. However, we can sometimes have a very difficult relationship. Let's say I want to know the time and a planet's position. You know, in our astrology, right? We're trying to say, okay, at a specific time of the year, where's the position? Where's the relative position between two stars or between the Earth and also like the sun? So of course, this relationship is relatively complicated, but nevertheless, this is actually a relationship. A function is just trying to help you guys review such a relationship and potentially find out the property of such a relationship. Right? I think this is a very primitive, very basic definition of a function. You guys should be quite understandable, right? From day one. Okay, as long as we know the first level of definition, it's time for us to go to the second level of definition. Because this definition is too human language, right? A relationship between one variable, one varying quantity to the other, it does not really give you too much information. How can we use a more mathematical way to give us such a definition and help us to understand the nature of the function better? This is exactly what the mathematicians is trying to look for, right? So that being said, we actually go to the second definition. The second definition, I think, is more understandable from our high school's perspective. And in order to understand the second definition, we're going to involve the set and also the map. So these are two basic concepts in our high school math as well, right? What is the definition for set? What is the definition for map? This is a higher class. I think you guys already have some basic understanding. So from a set, a map's perspective, how can I define a function? How can I use a more mathematical word try to present whatever we just defined using the primitive definition? So here's the second definition. A function can be defined as a map. We given map a denotation f. Okay, you can use whatever definition you like, whatever denotation you like, but most of the time we use f try to define such a function or such a map. Okay, this map is what? Is from set A to set B. Okay, a function can be defined as a map from one set A to the other set B. Okay, we mark definition as f A to B. Again, this is only a denotation, right? We just want to make sure this is f, this is my map. The map is actually defined from one set to the other set, right? From A set to B set. You see, because we use the word from set A to set B, so this is kind of a directional thing, right? From A to B and from B to A, these are considered to be two things. So therefore, we use such an arrow, right? Arrow is pointing from A all the way to B. Okay, so this is only a definition. We call this a function defined from A to B. Okay, A to B. Okay, you have such a mapping relationship from a set A to set B, then we can call a function is defined from A to B. So we can use such a denotation, y equals to fx. Well, x belongs to A, y belongs to B. Right? This is only a kind of like a denotation, right? We want to use this way, try to define a function defined from A set all the way to the B set. Okay, so here we want to give a very quick terminology. Here, A is called the domain of function fx. B is called the range of fx. Is it right? I think there's something quite understandable, a domain and a range. And why you talk about the domain and range? Because domain and the range are two sets. One is pretty much the x can take from, that's the domain. One is the y can take from, which is the range, right? This is the basic definition. Okay, and besides that, I think this is a very important concept as well, is that in order to call a map from A to B is a function, there is actually a very important criteria. You cannot just randomly take two sets, right? And then just make a ramping, and then you say, okay, this is actually a function. So what is the very important criteria in order to say a map is a function? We want to say for any given x belongs to A, right? I think we talk about it so many times. So this guy, this is only a denotation. It means for any given. This is actually derived from the word arbitrary, right? We just put A upside down, right? Arbitrary. For any given x belongs to A, there must be only one y belongs to B, such that fx equals to y. Is it right? For any given element from A, there must be one and only one y from B, such that fx equals to y. So how to understand that? Let's try to have a quick review. So at the very beginning, we're talking about the function is defined as a relationship from one set to the other set. Let's say this is A, this is B, right? Okay, so let's say I have an item A1, A2, A3. Just want to make our life a little bit easier, B2, B3. So there are different kinds of relationship for such a mapping or such a relationship. Sometimes, let's say you have something like this, right? So you have a one item from A, they can go to one item from B. Another item from A, go to another item from B. This is quite understandable, right? This is one way. Or you might have something like this. This is A, this is B, A1, A2, A3, B1, B2, B3. For instance, you might have from one value mapping to two values. Maybe one value mapping to two values. Maybe I'll give it B4. This is also possible. Let me try to give you a real example. Let's say we have a collection of our students. And we have a collection of our parents, right? So we just want to find, okay, A is the collection of our students, B is the collection of our parents. So we want to have this mapping from student A, where are the two parents of this given student? Of course, from one value in A, you will be able to find at least two, right, in the B set. So that is actually one-to-many relationship. One-to-many, right? It can be two, can be three, can be whatever. It really depends on how you want to define such a definition. But generally speaking, you can find one student and then all the way go to multiple items in the B set. So this is kind of a one-to-many relationship. Okay, what about something like this? I want to put the parents here. A1, A2, A3, A4, A5. And I want to put the student, right, on the B set. This is A, this is B. You have B1, you have B2, you have B3. Now the entire thing pretty much goes reversely. You can have two items from A set, and they're all pointing, or they're both pointing the one item in the B set, right? So father and mother of B1, they're actually in the A set. father of mother, father and mother of B2 from A to B, right? So on and so forth. You can find maybe A6, A5, all the way to B3. So this is more like a what? This is more like a many to one relationship. Okay? Okay, if we do a quick comparison, the first one we can consider this is a one-to-one relationship. Is it right? The second one is one-to-many relationship. And the third one is many-to-one relationship. Right? This is only an abstract, right? You might have more relationships, but generally speaking, you can classify all your relationships into these three different categories. Okay, so with that, my question is, which one can be considered as a function and which one cannot be considered as a function? Do you guys know this? Which one can be considered as a function relationship and which one cannot be considered as a function relationship? Anyone knows this? I think you're gonna learn, I think you should learn that in your regular school, right? As long as you learn the definition of a function. Okay, have you guys heard about it? How to find out a relationship, how to find out the relationship between two sets and define such a relationship is a function. So this is actually a very interesting question I like to show you guys. Even though function's primitive definition is basically very generic. As long as you have a varying quantity, you go to the other quantity, this is a function, right? You think this is kind of like too general. And then we go to the second definition. The second definition is pretty much using a set, right? A function can be defined as a relationship between two sets, set A mapping to set B. Well, set A, we'll call this is a domain. A set B, this is a range. But still, it looks like ABC, right? Looks like 1, 2, 3, these three different patterns. They're all good. They're all kind of like a relationship between A and between B, and that's it. However, my question is, can all of them consider as a function, or only a portion of them can consider as a function? This is actually a very, very important concept we need to clarify at the very beginning, okay? Because we just mentioned such a very important property. For any given x belongs to A, there must be only one y belongs to B, such that fx equals to y. So this is more like a mathematical language, right? But if I translate it into more human language, so this one means what? If I find an item from A, using your definition, using your relationship, you can find only one mapped item in B. Is that right? If there is one item in A, you must be able to find a mapped item in B. And there must be only one mapped item in B. Let's check it out. Is there anything for our three relationships? Can they all meet such a criteria or not? So the first one is, as long as I find A, there will be only one B, right? In the B set, such that A can be mapped to B. If there's another A, I find another B, another A, another B. Voila, it says what? So for any given element from A must be able to be mapped to only one item in B. So therefore, for sure, this is a function. Okay. What about the second one? If I find an element in A, I will be able to find out two elements in B, B1 and B2, and both of them can be mapped to A. So if that's the case, this is not what we required from here, right? Because there's going to be only one A. I mean, if you give me an A, there must be only one B mapped in the B set. However, if you give me one A, there are two B's in the B set. So therefore, according to the definition of a function, this is not a function. Is right? you're more like doing a relationship from one to many. One A mapped to multiple B's. I'm sorry, this is not a function. Okay, let's continue. What about the third case? As long as you give me an A, I can find a B in the B set such that FA equals to B. As long as you give me another A, even though these two A's, they're pointing to the same B, but it doesn't matter. According to our definition, as long as you give me an A, I can find only one B such that FA equals to B. Is it right? As long as you give me an A, I will be able to find a B. As long as you give me an A, I will be able to find a B. I don't really care how many A's they're mapping to the same B, but according to our definition, you give me one A, I give you one B. You give me one A, you give me one B. Voila. So therefore, that is also a definition of a function. So this actually goes to very important concepts we like to understand. In order to define a function, we all know that function is defined a mapping, right, by the mapping from set A all the way to set B. Okay, if this mapping is a one-to-one relationship, perfect, this is a function. We have no problem. If this is a one-to-many relationship, no, this cannot be a function. However, if this is a many-to-one relationship, no problem, you can still be a function. This is more like the clarification from the basic definitions perspective, right? If I want to give you guys some quick example, some example you are very familiar with, I think you should be able to understand it right away. Let's say for such a one-to-one relationship, a very good example, y equals to x or y equals to 4x, it doesn't matter, right? As long as you have x here, you times 4, you will be able to find only one y in the B set. As long as you find x here, you times 4, you will be able to find only one y in the B set. This is a one-to-one relationship. A very good example is actually a linear function, right? Okay, what about this guy? Many-to-one relationship. A very good example is y equals to sine x. We both know that, we all know sine x is a periodic function, right? So let's say I want to be, so sine x equals like this, right? This is a, okay. If we want to find out the x values such that y equals to 0, that is what? X will be equals to k pi, right? K can be an integer. As long as x is the whole number multiple of pi, then you can always have the y value equals to 0. So that being said means what? In order to map to 0, let's say b1 equals to 0, you not only have one y, you have infinitely many x's, right? As long as x can go to k pi, such a relationship, you will be able to define the fx equals to 0. Okay, so far, so good? So try to think about everything you have learned before. All your functions, all the functions you have learned so far, they can be classified either into one-to-one relationship or go to many-to-one relationship. But none of them can go to this one-to-many relationship. As long as you go for a one-to-many relationship, this is not a function. So far, so good? Any questions? Any questions, just let me know. Okay, perfect. If all good. So that's pretty much the basic definition of a function. So moving forward, we're going to try to talk about how to present a function. You see, we already find out, okay, function is kind of a mapping from one set to the other, but this is more like a human language, right? In our real mathematics, we don't like to use a human language all the time. On the contrary, we're trying to use kind of like mathematical way, right? More abstract way, try to denote a function. So the question is very intuitive. We know function is such a definition. How can we present a function? How can we denote a function? Is there different ways for us to present or denote a function? The answer is yes. So there are actually 4 different ways to denote a function. Let's try to think about it. The first one is actually we call it listing method. So what is a listing method? We just try to list out. You tell me function means a relationship between set A to set B, right? You tell me f, A goes to B. This is a function. Okay, I think the most straightforward way is, let me try to list them out. I'll give an example. Let's say we just finish our like a sentence, right? So maybe the Canadian population. This is actually a very typical way we can list them out. Let's say Canadian population can go like this. Maybe the year and the people in median. This is 2010. I only have the old data, 2012, 2014, 2016. Then you have this is 3412, 3506, 3568, 3688. Right? I think this is the most easy way. You just basically list out all the values, right? And put them into a diagram, into a table, and then you'll be able to see, okay, this is the relationship between A, right? This is your A. A is different years, and this is your B. B is the population for that given year. So everyone knows that this is the listing method. Okay. Number 2, because we're not so happy with listing them out, this is like too inconvenient, right? Sometimes if we do not want to list them out, we can actually use the graph. So the second one is the graph method. Using a graph, we can actually denote a function. There are so many examples. Let's say y equals to log 10x, right? This is a logarithm. Y equals to 3x squared. This is a parabola, right? You can basically give the graph. As long as you have the graph, you will be able to denote such a function. This one is actually more conspicuous, right? Instead of listing out all the values one by one, you directly give a graph, and you will be able to see the functions, the basic property, increasing function, decreasing function, symmetric property right away. And this is actually a favorite, kind of like a preferred way in our entire mathematics using the graph. Okay. Number 3, sometimes if a function is functions graph is very complicated, or they have like a lot of functions that are very similar regarding the graph, maybe using the graph method give a lot of a confusion, right? Because you do not really know what is the uniqueness of a given function. So the third way, which is actually the most favorite way in the entire our mathematical world, is actually using the analytical method. AKA, you want to find out the expression of a function, right? Expression of a function. That is like so many expressions, right? Just want to give an example. Let's say you can have sine x plus tangent cube x, something like that, right? As long as you can find out the expression of a function, then you basically know the most important of a function, right? As long as I give you an expression of a function, and you will be able to basically plot out the graph, right? Then you see the graph, and then you can basically list out, as long as you give me x, I'll be able to find a y, another x, another y. So therefore, you'll be able to have the listing method. So I think that is actually the most important things to present a function, right? Okay, a tiny discussion I want to talk about here is that sometimes for a function, it is kind of difficult for us to give an overall expression for the entire domain. Some functions goes like this. You know, for our sine x, this is very easy, right? This is our sine x, y equals to sine x. You can basically use one expression to denote the entire thing. As long as x belongs to R, that's it. But sometimes some expression, some function is pretty weird. Maybe it goes like this. I'll give an example. Let's say if the function is lesser than -1, it's kind of like a linear function. Oh, this is like a line. As long as the function is between -1 and +1, it becomes, I don't know, it becomes maybe like a sinusoid function. Okay? As long as the function is greater than 1, it becomes, I don't know, maybe it becomes like a parabola. Okay? Goes like this. I think this is quite possible, right? Some function, it is really difficult for us to define them using one expression across the entire domain. Because at a specific interval, right, the function can be a one shape, and then you go to the other interval, it becomes another shape, and then the other interval goes to another shape. So that being said, we need to break them into pieces. I can't use one generic expression to denote the entire domain, but I need to break them into different pieces. So break into different pieces. This is quite understandable, right? Let's say y equals 2. As long as x is lesser or equal to 1, maybe, I don't know, maybe this is y equals to minus x plus 6. Okay. As long as x is between 1, -1, and 1, right? Given this is maybe sine x. As long as x is greater or equal to 1, I give, I don't know, maybe x squared plus 6x plus 61, whatever, right? It is quite possible. Some functions, like I said, you cannot use one expression to denote the entire x domain, but you have to break it into different pieces. So we basically using such a way to present such a function. It goes for different sections. Is that right? So here we give a specific name for such a function. We call it the piecewise function. Piecewise function means the function is cut into different pieces. For each specific pieces, let's say here, I want to just talk about this part. This is just like a regular function, right? Nothing really special. Its only difference is that this function is defined in a specific interval. It's not the entire domain, right? I think this is something quite understandable. Voila, this is our number 3 way, using the analytical way to present the function. And the last way is using describe method. What is that? You know, like I said, some functions, it is easy for you to give an expression like here, right? And sometimes if it is difficult to give an expression for the entire domain, you can try to break it into different pieces as a piecewise function. But there are some functions, even though you break them into pieces, it's kind of impossible for you to find an expression. A very good example is the famous Dirichlet function. What is the Dirichlet function? Dirichlet function is something like this. Dirichlet function defines as dx. As long as x is a rational number, as long as x is a rational number, dx equals to 1. As long as x is an irrational number, dx is equal to 0. You see, such a function, our real numbers can be classified as two parts. One is rational, one is irrational. Is that right? Real numbers is composed by using rational numbers and irrational numbers. So normally speaking, we use Q to present rational. We use Q to present rational. Some students say, hey, why we don't use R? Because R is more reserved for the real numbers, right? So that's the reason we always try to, everyone knows that R is reserved for the rational numbers. So we use a different way. We use Q to present the rational. Like the R is more reserved for the real numbers. So we use Q to present the rational numbers. Then what about irrational numbers? Irrational numbers, we always use R minus Q, because R is the overall real numbers. Real numbers is basically add between the rational numbers and the irrational numbers. You use the real number to subtract the rational numbers. All the remaining will be irrational numbers, which is quite understandable, right? Let's say I have such a function. So this function, as long as x is a rational number, the function will be equals to 1. As long as the x is an irrational number, the dx will be equal to 0. Let's check it out. How can I give the graph of such a function? Let's think about it. So this graph will be a bunch of points, right? Let's say I just want to make your life easier. We just try to give the graph between 0 and 1. This is y, this is x. So how many rational numbers between 0 and 1? Infinitely many, right? How many irrational numbers between 0 and 1? Also infinitely many. But it's something just like this. If I wanted to use my point, so this is 1, this is 0. So the function graph is more like a bunch of points, right? And this is also a bunch of points. Why? Because we know that between any rational numbers, there will be at least one irrational numbers. Is it right? Between any two irrational numbers, there will be at least one rational numbers. You guys follow me? Yes or no? Can I have some quick feedback? Can I have some quick feedback? Yes or no? If you don't understand, please let me know. So there are infinitely rational numbers and irrational numbers, right? Between any two rational numbers, there will be irrational numbers. Between any two irrational numbers, there will be rational numbers. So that being said, if I zoom out, if I zoom this graph, there's going to be up and down very quick, right? Then you find a rational, the next one will be irrational, and then you also have a rational, so on and so forth. So the graph is actually jumping up and down fairly quick, just between 1 and 0. All the way comes to here. Do you guys understand me? Yes or no? Can I have some feedbacks? Yes or no? Hey guys, can I have some quick feedbacks? Yes or no? Do you understand me? Are you guys following me? Yes or no? The other students, any question, just let me know, okay? We're just trying to find you guys. If you have any question, we'll help you. I'm trying to help you guys find out a solution. Okay? Yeah, I think this is understandable. So that being said, this function is kind of like a big fluctuating up and down very quick, right? So you see, this a function, this is kind of very difficult for us to find out the expression of such a function, right? How can you use an expression like a y equals to what kind of x in order to present how such a function looks like? Is it right? So this is actually the fourth way how to present a function. Using the description method, you just basically describe it. As long as x is a rational number, x equal to 1. As long as x is an irrational number, dx is equal to 0. More like a human language. Okay, so here, I just want to give you guys a very, very quick side note about this Dirichlet function. The Dirichlet function is one of the most important functions in calculus. As long as you go to college, you learn advanced calculus, advanced algebra, you will get a lot of involvement with the Dirichlet function. I think one of the very direct application for you guys is pretty much for the integral. So let me ask you guys a quick survey. So I know some students actually went to AP. So you basically learned like the integral. So let me ask you, have you guys learned about integral already? This is from our day class. The North American math competition normally do not ask you the integral part. The calculus, like the derivation, like derivative, like the integral, generally speaking, this will not be tested in North American math competition. As long as you find a solution using integral, means there must be another, like a more easy way to solve the problem. You don't really have to use the integral. So let me ask you one, guys, can you give me a quick feedback? Have you guys learned the integral? Because if you do, I can give you guys a quick explanation regarding this importance of this Dirichlet function. So can I have some feedback? So don't be shy. If you do not learn integral, just let me know. So this is not, because like I said, our North American math competition, we won't focus too much on the integral. Okay, yeah, I see many students learn a little bit integral. Okay, just want to give you guys a very quick side note. You know, in the integral, you guys learn the entire our high school territory, right? We learn a lot of technologies, how to do the integral. So those integral actually has a name. That is called the Cauchy-Riemann integral. What is that? Cauchy-Riemann integral says, if you want to make an integral for a function, at least the function should be continuous. Is it right? At least the function should be continuous most of the time. So I give you a function like this, you'll be able to find out the integral, right? Integral is more defined as the area just below the curve, right? I give another function, goes like this. Okay, it is okay. You can do this integral. This is basically the area under this graph, under this curve. Then what about if you have something not continuous? In our case, let's give an example. In this function, like I said, any rational numbers, there will be irrational numbers in between. So between any ones, there will be a zero. And also between any zeros, between any irrational numbers, there will be a rational number in between. So between any zeros, there will be one. So that being said, this graph, oh my God, it's actually up and down, up and down. For every single point, this graph is not continuous, right? I think using our common sense, you can understand what I'm trying to say. Like the curve is never continuous. It's up and down like crazy. So that being said, you won't be able to use the Cauchy-Riemann's integral because you will not find like a real graph, right? A real curve, and then find out the area under it. So that being said, for such a graph, if you want to do an integral, let's say I want an integral from 0 to 1 dx, it is impossible for me to use the Cauchy-Riemann's integral. In that case, if I really, really want this integral, what can I do? I need to use the Dirichlet integral. So this is actually one of the applications for the Dirichlet function. So the Dirichlet integral, let's say for this guy, I just want to give a very, very quick side note. This guy, if I want to do an integral between 0 and 1, you see, this guy's up and down, you know, up and down so quick. If you want to do some guess, who can tell me what is the value for this? This is only like a guess, right? You're not obliged to know this. You know, this up and down so quick, right? So this is, if I want to do an integral, I want to find what is the area under this. Is it going to be 1? It's going to be 0, or some value between 1 and 0. If this is a whole line, this is going to be 1, right? If the line is here, this is going to be 0. But what if they're mixed together? This is going to be 0, or this is going to be 1, or something in between. This is actually a very interesting discussion in the entire maths. I think most of the students will find out some value between 0 and 1, right? Because you see up and down all the time. Actually, the value is actually 0. Why is 0? It looks like all those rational points, they have so many ones. These ones compared with the irrational points, it's almost nothing. You can ignore them. So this is actually also a very important concept. As long as you learn the real analysis, this is actually numbers does. So number does means that even though rational numbers and irrational numbers, there are both infinitely many, right? However, if you do a comparison, even though there are infinitely rational numbers, infinitely irrational numbers, if you do a comparison between the two, you will find out actually the rational numbers is almost nothing compared with the irrational numbers. There are way more irrational numbers compared with rational numbers. So that being said, if you want to do this literally, even though you find there's an infinitely many ones there, but trust me, if you do this integral, this is totally nothing. This one is more like to 0. Like I said, this is only a side talk for the guys already learned this integral, so you should be able to understand what I'm talking. For the other guys, no worries. This is totally beyond our North American math competition. Okay, so let's continue. So we actually introduced there are 4 ways to present a function, listing them out using the graph, using the analytical way, and using some described way, right? I think most of the functions we have learned so far, you can use both of them. We can use all of them, right? Any way can be used for our functions. Okay, so that's the number 4 part. Number 5 part, we want to talk about, there's another type of function. Let's say, I want to give an example. Let's say gx. Let's say fx. Let's say we have fx. So fx equals to what? Fx equals to x squared. Okay, I define fx equals to x squared. Gx, 2x minus 1, right? I just want to give you 2 very basic functions. One is equals to x squared. The other one is equals to 2x minus 1. Okay, if you have these 2 functions, I want to do something like this. F gx. I think you guys should be very familiar, right? You see this all the time. So how to do f gx? F gx means what? Okay, at the very beginning, I want to use x as my variable, right? And then I can use x to present x squared. But x is only a box, right? The x, you can put 1 here, you can put 2 here, you can actually put another function there. So that being said, I'm just going to replace my original x using another function, gx. So my function is going to be what? X, this is a big box, square, but now this big box is no longer number x. It will be replaced using gx, 2x minus 1, perfect square, right? Okay, similarly, then what about gfx? Gfx, I said gx is something like this. This is only like a presentation. X, you can put 1, you can put 2, you can put whatever things under x. X is just like a box. But for now, what you're putting into the box, you're putting fx into the box. Fx is x squared. So this is going to be 2x squared minus 1. Is that right? So all the way you find out, as long as you have 2 functions, fx and gx, you will be able to create another function by cascading them together. If I use the word cascade, right? You can cascade some together. You put one into the other, or you put the other into the other, something like that. You will be able to find new function, to construct new functions, right? So I think you guys should learn this in your day school. So this is actually, we just want to give a name for this kind of function because this is the composite function. Composite function, I think the name speaks for itself. Composite means you compose a function, or this function is composed by using one function or by using two functions or multiple functions, right? So it is possible we might have another hx. You can have f, g, hx, right? You can name a few. You want to do all different kind of combinations, so on and so forth. As long as you can compose a function using multiple functions, we will say this is a composite function. So far, so good? I think this is also a very understandable thing. And the composite function is tested from time to time in our American and Canadian math competitions. Later, I'm going to be able to show you guys some real examples. All right. So a quick thing I want to give you guys a side note is that, you see, fgx, gfx, one is equal to here, one is equal to here. So that being said, in the composite function, the order matters, right? In composite function, order matters. fgx, normally speaking, does not equal to gfx. Normally speaking, there are some exceptions, but normally speaking, the way you compose, right? Which one is inside, which one is outside, makes a big difference. You cannot confuse them two. Okay, so far, so good? I think this is quite understandable, right? Nothing really tricky. Okay, so these are all considered to be the basic things. I think you guys should already have a lot of knowledge, so we don't want to unfold too much. Number 6, well, we want to teach you guys the very important elementary functions. We have learned many functions so far, right, in our high school territory. Actually, from the entire math perspective, we classified 7 types of function considered as the elementary function. So this is why we use the word elementary, just because these are considered to be the foundation of all the functions. In our Canadian and American curriculum, we give a name function and advanced function, but this is more like our way how to say that. But this is not a typical, this is not a standard way for the entire, or should I say, this is not a mainstream way, like to say the entire class, like the entire functions. In our entire math territory, we use the word elementary function to classify all the functions. So there are 7 types of elementary functions. They are considered to be the most important elementary functions. So what they are power of x. Let's say x to the power of 1, x to the power of 2, 3, all the way, whatever, k. Power of x. Roots of x. Under root, under 3 root, 4 root, all the way k root. This is understandable, right? Even though you might not be so familiar with the high order roots, high order exponents, but you got an idea right away. Exponent function. A to the power of x. Logarithm function. Log ax, right? I think you might not be an expert for every single one, but I think at your age, you should at least heard about all those functions. Trigonometry function. Sine x, cosine x, tangent x, so on and so forth. Inverse trigonometry function. Inverse trigonometry function, something like arc sine x, arc tangent x, arc cosine x, so on and so forth. Yeah, a very quick talk in this part. In our North American math competition, the inverse trigonometry function is not that much important. Yeah, we also tested sometime in AMY, but normally speaking, you won't see this part very often because the entire trigonometry part in North American competition is very important, but the inverse trigonometry function, because we do not learn that too much in our day school, so AMC, all those kind of math competition, they won't test it too much. For a Canadian exam, you just barely test it. So I think that being said, you don't really have to spend too much efforts for this inverse trigonometry function. And the last one is hyperbola function. Hyperbola function is more like y equals to ax, right? We know this from day one. Or something more generic, y equals to ax b over x. So this guy, we give a name. This is a Nike function. A Nike function, just like the brand Nike, because the shape of this graph is just like the Nike logo. So we give a name, Nike function. For the ones you are not so familiar with the Nike function, no worries. We will talk about it in our fraction function. Okay, in our coming lectures, we have one lecture talking about the fraction function. This is going to be one of the very important fraction function. So if you're not so familiar for now, no worries. We're going to talk about it in our upcoming lectures. So generally speaking, these are the 7 very important elementary functions. A lot of advanced functions, they can be elaborated or they can be derived using the combination of different elementary functions. So that's the reason why, you see, most of these elementary functions, most of them you have already learned so far, right? So these are actually considered to be a foundation for our entire functions. Okay? A student actually has a question. So why in our curriculum we say this is advanced function? Yeah, I totally understand you. These functions, the exponents, the logarithm, the trigonometry, in our Canadian and American curriculum, we call this advanced function. But this is more like a North American way to call it. In the real math world, these are all considered to be elementary function. Advanced function is only our book want to make a quick kind of like a quick difference between what is the elementary function, what is the advanced function. But generally speaking, the entire function, they both have a name, elementary. You can say some of them are more easy or some of them are more advanced. That's not a big deal whatsoever. So far, so good. Any questions so far? Okay. I think these are a very basic understanding, right? We must have learned this for a long time, but for our lecture, we always want to take the opportunity, help you guys summarize all the concepts together and try to make sure that you guys can, get a clear view about all those diagrams, all those concepts. Okay. After talking about our concepts, we're going to give you guys a very quick summary. In the function basic part, whenever you go to the math competition, normally speaking, what they're trying to test you. So the second part is problems. Because like I said, this function basics, you don't really have too much flowery things. So in the math competition, they won't test you something too crazy as well. So basically speaking, they will test you only three very important things. One is determine a domain. I give you a function, I ask you to determine domain. One is determine a range. I give you a function and then I ask you to determine range. The third one is kind of using some graph. The question might give you some graph of a function or how this function's graph looks like. And then taking from there, you'll be able to try to, determine some specific properties. So generally speaking, these are the three major categories the question might test you in a real math competition. So I think for the domain and the range, there's nothing to say. You just basically calculate, right? And for the graph, sometimes they can, they can give you one piece of function, right? Just one piece of graph, ask you to do something. Or they might give you some piecewise function. Like I said, the graph might go for different, I don't know, different 3 segments, right? Ask you to do something during these 3 segments. And sometimes they might ask you to do some composite function. Kind of like a combination, right? Between some easy functions, try to compose it all together and taking from there, solve the problem. So generally speaking, I think for the problems you're looking at for the function basics, there are no more but these 3 categories. They won't test you something too complicated rather than these 3 categories. Okay? So that being said, let's try to give you some real problems from a North American math competition. Try to see how we're going to deal the problems in these 3 different categories. All right, so after the technology, it's time to see some real problems. And then taken from there, let's see how to use the technology to solve the real problems. So let's jump to here. So problems. The first problem we're looking at is a problem. Okay, let me give you this problem. The first one is a problem. Let's have a look at our AMC problem. That's 2008 AMC 12A, question number 12. That's a relatively easy problem. We'll say as a warm-up problem. Okay, let's have a quick look how we're going to do for such a problem. So the problem says a function f has domain 0, 2 and has a range 0, 1. Okay, so this is a domain range related problem. And the notation AB denotes x is between A and B. Yeah, I think everyone knows that. Then what are the domain and the range, respectively, of the function g defined using 1 minus fx plus 1? So f is x between fx, right? Between 0 and 2. Y is between 0 and 1. Okay, now you have a gx, 1 minus x plus 1. Same thing, I want to ask you where x from where, from what to what? And what about y? Y is actually g, right? From what to what? Okay, 30 seconds. I'll let you guys think about it. Think about it. How are we going to do for such a problem? a function f has a domain 0 to 2, has a range 0 to 1. With all those information, the question asks you to define or to determine what is the domain and the range for a new function, gx equals to 1 minus x plus 1. How can we deal with such a problem? This is like a warm-up problem. So please, everyone, if you know the answer, try to type it into the group chat, and then we'll be able to see your answer. Okay? I think for such a problem, we always can start with the definition, right? This is like a domain and range. This is nothing but a definition. So let's just try to think about the definition. The definition said fx domain is 0 to 2. So that being said means what? If I have this f here, like I said, here can be x, can be whatever things, right? This is only like a black box, right? Everything can leave there, is that right? So if everything can leave there, that being said means what? That being said, everything leaves there, they must follow this criteria, 0 to 2, right? Today you have x, tomorrow you have x plus 2, like maybe like the day after tomorrow you have a gx, whatever. As long as you have something leaving under f, you must follow the criteria. Everything within the box should be between 0 to 2. So the box should be between 0 and 2, right? This is very understandable. Also, everything that you have f here must be between 0 and 1, right? As long as you put a f, the f's range is always between 0 and 1. There's nothing flowery. You just basically follow that criteria, and that's it. Okay? If that's the case, let's check it out. What's going to happen when you change this into 1 minus fx plus 1? Again, for now, your fx is no longer dealing with x. You're dealing with x plus 1, right? But like I said, as long as you want to make anything under f, I don't really care it's x, x plus 1, x squared, x whatever. As long as you leave that box, you leave in that box, you must follow this criteria from 0 all the way to 2. Is it right? So if you want to put a value x plus 1, no problem. Your x plus 1 must be between 0 and 2. AKA, your x must be between minus 1 and positive 1. So far, so good? Your x must be between minus 1 and positive 1. And the question asks you, what is the x? X is between minus 1 and positive 1. Okay? Second, the question asks you, what is the domain for, or what is the range for gx? Okay, even though for now, your gx becomes a little bit fx plus 1, but like I said, I don't really care about this f blah, blah, blah. As long as you give me an f, regardless whatever you have under f, you always have the total function value between 0 and 1. Is that right? So that being said means what? Your fx is between 0 to 1. Your f whatever, I don't really care. Always between 0 and 1. Is that right? So if that's the case, it means the function give you what? Fx plus 1, regardless whatever, x plus 1, x plus 1 million, makes no difference. Still between 0 and 1. Because like I said, everything you falls under f, you will always make sure they are between 0 and 1. I don't really care what is inside, as long as you see f, 0, 1. So that being said, fx plus 1 is between 0 and 1. So minus fx plus 1 minus 1, 0. So 1 minus f plus 1, 1, 0. What is 1 minus f plus 1? 1 minus f plus 1 is your gx. Gx. So therefore, gx is between 0 and 1. So far, so good? This is only using the definition. Nothing really flowery, nothing really crazy. You just basically use a definition. Is it right? So therefore, x is between minus 1 and positive 1. Gx, or your range, is between 0 and 1. Do we have the correct answer? Yeah, B part is our correct answer. So far, so good? Using the definition, nothing flowery, nothing complicated. You're just using the definition, and that's exactly what you need. Okay, so far, so good? This is our question number 1. Okay, if all good, let's go to our question number 2. Our question number 2 will be a little bit more difficult than our question number 1. All our problems are well designed. The complexity is growing up progressively, not crazily, progressively. The second problem, you're looking at a problem from 2006, AMC 12A, question number 18. Let's check it out. How are you going to do the second problem? The problem says the function f has a property that for each real numbers x in this domain, 1 over x is also in this domain. What does it mean? It means that, let's say, x is in the domain means fx is reasonable, right? If you find that x is outside this domain, of course, this is not going to be reasonable, right? Okay, as long as x is in the domain, fx is reasonable, it is definitionable, and 1 over x is also in the domain. Let's say as 5 in the domain, 1 over 5 is also in the domain. 6 in the domain, 1 over 6 is also in the domain. So these two guys, they're all definable, right? They're all definable, okay? And the most important thing is you always have fx plus f1 minus x, 1 over x equals to x. First of all, fx, f1 over x, they're both definable. Second, putting them together equals to x. This is like a property. With all those information, the question says, what is the largest set of real numbers can be the domain of x? This sentence, what does it mean? What is the largest set of real numbers that can be in the domain of f? What is the question is trying to ask? A lot of students get confused because they don't really understand the question. The question says, okay, I have fx. Fx have some special properties already given, right? And then the question asks, what is the largest set of real numbers that can be in the domain of x, of fx? So that sentence, it actually means what? The question just want to ask you, what are the potential values of x, right? All the potential values of x. The question, what is the largest set? Means you do not only tell me 1 or 2, you tell me everything you think possibly, like that is possibly be the domain of x, right? X can have one number, can have 1 million number. If you have 1 million number, you tell me them all, 1 million. I want to have the largest. If you miss 1 or miss 2, no, this is not the largest. So the question is really asking you, what is all the possible all the potential values of x, make sure this equation, let this fx hold. Right? I think this is very understandable. So this problem is actually an easy problem. However, this problem reveals a very important mathematical thought I'd like to talk with you guys. So this problem per se is fx, f1 over x equals to x. That's the only condition, right, given by the problem. And you need to find all x values. Okay. So before we jump to the solution for this problem, let me ask you guys a quick observation. When you read such an expression, fx, f1 over x equals to x, it really gives you a kind of feeling or not. It's kind of, looks like x and 1 over x, they're kind of symmetric. Is that right? X, 1 over x, they're symmetric. Symmetric means you can replace x using 1 over x, or you can using 1 over x replace x. So these two numbers, they're kind of have the same position for the entire expression. Is that right? Can I have some feedbacks? Do you agree with me, or you totally do not agree? Can I have some quick feedbacks? You can post your answers into the group chat. So don't be shy. I'm monitoring the group chat. Any question, any concerns, just let me know. Do you have any kind of like a feeling that x and 1 over x, they're kind of symmetric to each other? Is that right? If I use x, I replace 1 over x, the entire expression does not really change too much. Yes or no? Can I have some feedbacks? I think today people are really extra silent. No one really talk. Don't be shy. It's the first lecture. People may be a little bit like shy, but no problem. No need to be shy. Any question, just let me know. So far, so good? Yeah, I think everyone we're on the same page. As long as you find something symmetric, we're going to teach you guys a very important strategy. As long as you find something symmetric, you always want to do some construction or replacement. As long as you find in the problem, you have something symmetric, you always want to do some construction and replacement. Try to use this symmetric nature and you will be able to solve the problem. Let's try to see. I have fx. Right? This is what I have. Like I said, x and x minor, x and 1 over x, they're exactly identical for this problem. So that being said means what? As long as I replace x using 1 over x, the original expression still hold. Is it right? So my second expression is just replacing x using 1 over x, and the entire expression hold. Voila, check it out. You have two equations now. The left-hand side, they're essentially the same thing. Fx plus 1 over x, f1 over x plus fx. And the right-hand side, one is x, one is 1 over x. Therefore, x should be equal to 1 over x. Is it right? So therefore, x equals to positive 1 and a negative 1. That's it. That's all the potential values you can get for x. You just want to solve an equation of x, right? Taking from there, you tell me how many values for x. And this is your two equations. And you can solve out x is equal to positive 1 and negative Very understandable. Is that right? Very understandable. So therefore, the question asks you all the values of x. You know what? You don't have too much, only two values, +1, -1. So the solution for this problem is number 5, E part. So far, so good. You see, the $1 million part is you want to do such a construction and replacement. Just try to use this property, do such a quick thing, and you will be able to solve the problem. Okay, this is a AMC problem. Let me try to give you another problem using exactly the same strategy. Okay, this is an extension, right? The problem we're looking at is 2001 Japanese Junior Math Olympiad problem. Let A, B, C equals to 1. A, B, C, they're all positive numbers, 3 positive numbers, the product equal to 1. Determine the value of the following expression. Let's check out this problem. You have 3 positive numbers, real numbers, right? The total sum, the total product is equal to 1. And then the question asks you to determine the value of the following expression. A over 1 plus A plus AB. B over 1 plus B plus BC. C over 1 plus C plus CA. You see, this is also a rotation, right? This is also symmetric, kind of like AB, BC, CA, right? This is kind of symmetric. And this symmetric is even more because they're kind of rotating, right? AB, BC, CA. So we actually give a name. This is the cyclic. Cyclic. Cyclic means what? Rotation symmetric. So the meaning means rotational symmetric. Means A, B, B, C, C, A, they're kind of doing a rotation, right? Everything is symmetric. But there's not only 2 numbers, there are 3 numbers, rotational symmetric. And the question is asking for you, what is the value for such an expression? What is the value for such an expression? Okay, first thing first. Strategy. Problems, right? We like to talk about strategies in this. First thing first, if this is an Amy problem, who can tell me what is the faster track to solve this problem? If this is an Amy problem, who can tell me how can I solve the problem in about 30 seconds? Question number 1. If this is an Amy problem or AMC problem, it doesn't matter, right? How can I solve the problem within 30 seconds? Because Amy is like Amy is not a multiple choice, right? But still, you only have to show an answer, right? From 0 to 99, right? You don't have to give too much flowery explanations. AMC is multiple choice, right? You do not really have to show your work. Who can tell me if this is an Amy or AMC problem? How can I solve this problem within around 30 seconds? Who can tell me? I see somebody has the correct answer already. Yeah, you can post your answer into the group chat. Okay, no problem. You can raise your hands. You can. Yeah, if somebody want to answer, you can. Yeah, you can raise your hand. Maybe I'm gonna ask some student to basically unmute yourself. Right? You can give us the answer. Who would like to say something? I see somebody raise their hand, so because it was like too fast, so I didn't really catch who raised their hands, who raised his hands. If this is Amy or AMC problem, how can we solve it right away without spending too much time, too much efforts? Yeah, I see somebody has the answer right away. Amy and AMC, there are multiple tries or something, just give a number, right? They don't really need you to show the work. So in order to make it working for Amy, you just let A equals to B equals to C equals to 1. And that's it. Is that right? Because whatever number ABC here, we don't really care, right? You just give three numbers, 1, 1, 1. 1, 1, 1, they're all positive, and the product equals to 1. And then you just plug in the value, 1 over 3, 1 over 3, 1 over 3 equals to 1. Voila, that's the solution for this problem. So far, so good? That's our shortcut way to solve the problem. Then what about the real solution, right? If this is a Canadian exam, they won't ask you to do any shortcut. You need to give a real solution. Now, how can I do a real solution? Okay, I think the most challenging part is that, you see, all the denominators, they're not the same. Well, I think one of the crazy way is you just want to do a huge thing, put these three denominators together, then A will be two things, B and C. Is that right? So that will be a real hardcore solution for this problem. Do you guys agree with me? Yes or no? I think that one you have no concern, right? You just do a hardcore calculation. So cross your fingers, hopefully you can do it correct. Everything will be canceled, you get what you need. But that's like too low efficient solution. How can we use this symmetric property, especially rotation symmetric property, help us to kind of get rid of this weird denominators, make our denominators looks better? That's $1 million question. Is that right? That's $1 million question. So let's try to find out a very smart way to solve the problem. Because like I said, as long as you see the rotational symmetric, one of the key points is doing what? Is trying to do a construction and replacement. Construction and replacement, right? This is what we mentioned here, construction and replacement. How can I do a smart construction and replacement to make our life a little bit easier, while AKA try to handle the denominators better? This is actually the solution. A times B times C equals to 1. We can let A equals to what? X over Y, Y over X, same thing. B equals to X over Z. C equals to Z over Y. Of course, X, Y, Z, they're all greater than 0. Because doing this, you'll be able to make sure A times B times C equals to 1, right? There's nothing really, there's nothing really contradiction, right? You just want to make everything, add a multiple of them that together equals to 1. And also, as long as you do this, you know what? Let's try to plug in everything into the first expression. Okay, A is equal to y over x. B is equal to x over z. There's no trick. You just basically do a hard calculation. Plug into equation. The first one, a 1 plus a plus b, will be equal to yz, xz, yz, yx. No trick, just basically plug in the value. And then you put into a second one, 1 plus b plus bc, it goes to x, y, xz, yz, yx. The third one, zx, xz, yz, xy. There's no trick. You plug in the value, that's it. Wow, automatically you find out. Check, look at this. All the numbers, all the numeric denominators will be the same. Adding them together directly equals to 1. Well, you do a very, very quick substitution. You see the complexity of the problem has been reduced significantly. Well, I have to say, doing this replacement, doing this substitution, you need a little bit inspiration, right? Some sparkling in order to make it work. But generally speaking, is that you want to use this construction and replacements nature. Try to see how can I make A, B, C, these three guys, they're rotational symmetric. So I think this is a very good way to maintain this rotational symmetric. And as long as you plug in, you will be able to cancel a bunch of numbers and make sure all the denominators, they're exactly the same. And taking from there, you can add them together. This is, I think, one of the very important things I want to show you guys. And this strategy is actually very common from time to time. You can see that in many kind of math competitions. So this is actually a very important strategy. So far, so good? Yeah, this is pretty much using a kind of things to determine like a range, right? This is also can considered as asking a range for this guy, but the range is only one guy, it's like only one number. But you're trying to use this symmetric property to doing the construction and replacement, and you're good to go. Okay, if all good, let's go to another problem. Another problem we're looking at let's try to go to a Canadian problem, right? Not all the American problems. Let's go to a Canadian problem. So this Canadian problem is a problem that comes from 2005 Euclid question number 8. It's our Waterloo Euclid problem. So let's check it out. So like I said, in today's problem is pretty much domain, range, graph, right? Let's check it out. A function is defined as follows. You see, this is what? This is like a piecewise function, right? The function has 3 parts. Whenever x is less than 4, it's 4. 4 to 5, minus 4 to 5, it's minus x. Greater than 5, it becomes minus 5. Just basically 2 constant functions, and then include such a linear function. Okay, on the grid in the answer booklet, try to sketch the graph of gx equals to under root 25 minus x absolute, and then make a square and state the shape of each of the graph. Okay, how can I get the graph of this given fx is kind of like a piecewise, right? This is a piecewise. You know what? A piecewise function, like I keep saying, is nothing but a combination of 3 different parts. Yeah, maybe 3 parts, maybe 5 parts, I don't care, but a bunch of parts. So generally, if you see the entire function at one shot, It might be a little bit drowsy, here and there. But if you jump to each specific piece, these are considered to be just a regular function, nothing really special, right? If that's the case, let's just try to do it one by one. Let's check it out. Piece by piece, how are we going to do this? A piecewise function, you always have to break into pieces, right? Don't get confused for the entire thing. You need to basically break it into different pieces. So let's check it out, how we can break it into different pieces. So you're trying to do a function gx equals to 25 minus fx. So gx equals to under root 25 minus fx, absolute value, right? Perfect square. Again, I want to try for 3 area. X minus 4, x lesser than minus 4, x greater than 5, from minus 4 to 5. Let's check it out. As long as x is lesser than minus 4, fx is a constant function, right? Constant function, that's easy. 25 minus constant, full perfect square, right? So that one is what? 3. So that being said means gx, as long as x is less than minus 4, gx is a constant function. The middle part, I'm going to leave it here for a sec. Right? Let's try to do some easy part first. As long as x is greater than 5, fx is a constant function. 25 minus 5 perfect square. This is 0. Oh, voila. It means as long as x is greater than 5, gx is also a constant function. This time it's a 0. So this function looks like what? Let's try to have a graph here. Oh, oops. For the one in the middle, let's just leave it there. Let's try to do some easy thing first. So this is my thing, my x, y, right? So this is my y, this is my x. As long as x is minus than 4, this is minus 4, right? And this is positive 5. Okay? As long as x is less than minus 4, the entire gx equals to 3. So maybe something like this. This is 3, right? Maybe my graph is not so good. Let me try to erase it. 3 should be lesser than 4, right? Something like here. Right? As long as x is lesser than minus 4, it's this part. As long as my x is greater than 5, this part. Okay, these are all easy peasy stuff. Well, the most challenging part is whatever is within this little range. So we're gonna see. As long as x is from minus 4 all the way to the positive 5, my fx becomes negative x. So my expression goes to what? 25 minus x squared, right? So minus x can be just simplified as x squared, right? That makes no difference. Y equals to 25 minus x squared under root. So I'm just gonna drag this part out. This part means what? Gx equals to under root 25 minus x squared whenever x is between 4 and 5. What is that? Let's check it out. Gx, I use y, right? Y equals to 25 minus x squared minus 4 to 5. So I just basically do a perfect square, right? There's not too much I can do. Y squared equals to 25 minus x squared. So that means that x squared plus y squared equals to 25 whenever x is 5 minus 4 to 5. Voila. Who can tell me What is that? X squared plus y squared equals to 25. Well, x is from -4 all the way to 5. That's a circle, right? That's a circle. X squared plus y squared equals 25. That's a circle. It's like the circle center is the orange, and the radius is 5. But bear in mind, because this part, you have a under root 25 something here, so the entire y should be greater than 0. Is it right? Even though all the way let me try to change a different color. All the way comes to here, you will see y is greater than 0, right? So if you're talking about the circle, it's only half of the circle, the upper half, not to say the lower half, right? Because y is actually positive, under root 25 minus x squared. So your graph in the middle is pretty much something like this. You're trying to find a circle, right? But that circle is actually here, right? This is the circle. It's only the upper part, right? Because you only cut from -4 to 5. You only cut this half, right? Not the one beside, not the one just beyond this -4 to 5, right? You only cut the one in the middle. And don't forget, you're only taking the upper half because y is equal to under root 25 minus x squared. It's a positive type. So that being said, that is your final answer. Your graph looks like here. It's a piecewise function, right? And basically, this is the graph. You see? It's just basically using the definition. You're not doing something too crazy, too flowery, right? You just try to solve the problem using the definition. And that's it. Okay, so far so good. So this is actually use a piecewise function. Like I said, piecewise, there's nothing special. You just break it into 3 pieces. And for each piece, you just do like whatever you have to do for regular function. Nothing really special. All good? All right. If all good, let's go to maybe the last problem for today's lecture. Okay, let's go for an Amy problem. Our complexity is going up. Let's go for Amy problem. Again, using the basic concepts, we'll see how we're going to do a Amy problem. Number 2, there you go. That's the Amy problem. That's a problem from 1997. That's an old Amy problem. Amy 1. This is Amy, yeah, because by the time then there's no Amy 1, Amy 2, there's only one Amy. 1997, Amy, question number 12. Okay, almost the last 3 problems. Okay, so let's check it out. Every single step using the definition. So the question says, function f is defined by using ax plus b over cx plus d. It's a fraction function, right? But no, we're not using any flowery things from fraction function. We just, okay, take it as a function. Where a, b, c, they're non-zero real numbers. Okay, non-zero real numbers. Nothing really too much. Has the property f19 equals to 19. f97 equals to 97. I think all the way comes to here. You need to have some kind of vigilant. As long as you see this, it looks like the question give you 2 guys, right? 2 fa equals to blah, 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 fb equals to blah, blah, blah. But there's not, just like a random A, random B. Just you see, this guy is always the same as this guy. This guy is always the same as this guy. Is it right? We don't know how to do this, but just put it there. Maybe later we'll figure out. You need to be very sharp as long as you're reading it. Every single number, they're not giving for fun, right? There must be some underlying reasoning for that. Let's just try to think about it. There might be something interesting for that. Later we can check it out. Okay, and fx. This is a what? This is a composite function, but it's not composite with the other function. It's just composite by itself. right? You just f apply to fx equals to x for all values except minus d over c. Okay, I don't really know what it is. Let's just put it there, okay? Then find a unique number that is not in the range of f. What does this sentence mean? The unique number which is not in the range of fx. It looks like the range of fx is super big, right? It basically covers everything. Only one number is not in the range. Is that right? Only one number is not in the range. Let's just try to find out that number. Okay, so for such a problem, I think you don't really have too much things to get started. The very important thing is you have fx equals to x. That's the most important condition for you to get started, right? There's nothing really special. So let's just try to just plug in the value, right? So because fx equals to this, so ax plus b, cx plus d plus b, c, ax plus b, cx plus d, c, and d, right? Equals to x. Is that right? You just plug in the value. There's no trick you can do. Okay, as long as you have this, I think you just do some quick simplification. There's nothing you can do too much. So I'm gonna save the time. You simplify this equation, you go to here. You need some time to do some calculation, but this is not a rocket science. You should be able to figure it out. Okay, just a quick simplification. That's it. Okay, so this function says what? This function is good for all the values except x equals to minus t over c, right? This is what the question says. This guy hold for all the values except x equals to minus t over c. It means this guy hold for all x value except minus d over c. Except for minus d over c. Let's check it out. You want to make sure this guy plus this guy plus this guy equals to 0 for all the x number. X can be 1, can be 2, can be 1 million, 3 million, can be whatever you want it to do, as long as not minus d over c. But is it possible? Because x is changing all the time. How can I make sure every single x I want to make this expression hold? Is there a way to make this expression hold for all the x's? You see, this is a variable. This is a parameter, right? Times x squared. This is another parameter times x squared. This is like a constant, right? I want this guy hold for all the x's except only one. But at least I can have 1 million, 3 million, 1 trillion x for this guy hold. But how can I make sure x is changing? To make sure this guy holds for all the x's, there's only one possible solution, aka this guy must be equal to 0. This guy, they both equals to 0. As long as I have 0 times x squared, 0 times x plus 0 equals to 0. That being said, you can choose whatever x you want to choose. I don't really care. Regardless, you give me whatever x, always hold. Is that right? That one makes sense. So that being said, a plus b times c equals to 0. d squared a squared equals to 0. b a plus d equals to 0. Is that right? Oh, so that being said actually means what? It actually means what? As long as this guy equals to 0, d plus a, d minus a equals to 0, right? Because you're telling me that d plus a, b, c, d, they're non-zero real numbers. Non-zero real numbers. This guy might not be always equals to 0. So, I mean, like, because you want to have like d, the non-zero real numbers. Let's check. So either d plus a equals to 0 or d minus a equals to 0, right? But as long as d minus a equals to 0, d equals to a, that's a very strong condition. You want to make sure d is a, they're always the same, right? So maybe you can go for d equals to minus a, right? There are only two possible solutions, either d equals to a or d equals to minus a. Okay, no problem. Let's put it there, okay? These are the two possible solutions, right? That's what we can get all the way from here. Moving forward, I think that's pretty much what I can get from here, right? Is there some other conditions we do not use them yet? F19 equals to 19. F97 equals to 97. Let's check it out. F19 equals to 19. F97 equals to 97. So that one means what? You have AX plus B, CX plus D. That's for FX, right? This guy and this guy looks like FX equals to X. Is that right? Because 1977, I mean, like 97 and then 97, they're almost like the same thing. Fx equals to X. So that being said, maybe I can say something like this: 19 and 97, they are the two roots of ax squared plus b, cx squared plus d equals to x. Is it right? This guy, they can both classify it as fx equals to x. So that being said means what? Means these two guys are actually the two roots of such an expression, right? This guy is a quadratic equation, right? So this equation actually has two roots. One is 19, one is 97. Is it good? So therefore, I do a quick simplification. 19, 97 are the two roots of this guy. I'm going to do a quick simplification. It goes to cx squared d minus ax minus b equals to 0. As long as you have two roots and the quadratic equation, first reaction is doing what? Vieta's formula, right? You're going to have what? The two guys, adding them together equals to minus d minus ac. The two guys, multiply them together, minus b over c. Is that right? Don't forget, you just calculate d is equal to a or d equals to minus a, right? Trust me, using all of these guys, you will be able to find a relationship between a, b, c, d. Of course, you won't be able to solve it because you have 1, 2, 3, 4 variables, but you only have 3 equations. You won't be able to solve it, but you can find a relationship. So one of the relationship is d equals to minus a equals to 58c, b is equal to minus 1843c, d is equal to minus 53c, minus 58c. The other, this is basically on this part, right? D is minus a. As long as d is equal to a, you will find something abnormal because you cannot have something like this. Check it out, go back to here. Oh, oops, where's the problem? Yeah. Okay, so like the problem is here. Let me just try to give you the problem. For some reason, the problem is gone. Oops. The question says you cannot have all values except minus d over c. Okay, do some quick analysis. You can find out this guy does not make sense. Okay, so this is basic plug-in value. You'll find it out. So that being said, that's the only possible solution for this ABCD. Like I said, you won't be able to solve ABCD, but on the contrary, you can actually find out the relationship between ABCD. So fx is what? Our fx is what? ax plus b, cx plus d, right? Plug in the value, you can get 58x minus 1843 x minus 58. Do a quick simplification. 58 minus 1521 x minus 58. So that being said means what? It means that I will never ever fx, right? fx equals to this guy. I will never ever take 58 as my fx value, right? Is that right? In order to make 58 as my value, this guy has to equal to 0, but this guy can never be equal to 0. Is that right? So therefore, 58 is the number that fx can never reach. Okay, what the question asking you for? The question asks you to find out the number, unique number, which is not in the range of fx, aka this is your 58. So far, so good? I think it's quite understandable, right? So you just try to do this composite function using the Viatas formula a little bit, find out the relationship between A, B, C, D, whatever, and taking from there, you will get the expression of fx. And then you can get, okay, fx can never reach this 58. And that is the number fx cannot take. So far, so good? You guys follow me? Yes or no? Can I have some feedbacks? Hey guys, can I have some feedbacks? Yes or no? Okay, perfect. Yeah, I think that wraps up our today's lecture. Our today's lecture is our lecture number 1. We just want to give you guys some basic understanding for function. We introduced the definition of a function. What is the range? What's domain, right? And what is the graph? And in the graph part, sometimes it's a composite function, sometimes it's a piecewise function, but none of them are so strange or so complicated. You just plug in the value. Either plug in the value for the composite or just try to break them into different pieces. And overall, you will be able to have a quick understanding for this composite or this piecewise function looks like. Yeah, I think that's pretty much what I want to say for today's lecture. So I'm going to upload an assignment to our Google Classroom. And in the next lecture, we're going to talk about a second lecture of function. We're going to talk about some increasing, decreasing, some kind of odd function, even function, and some basic properties of a function. All right. So you have any questions for me? So generally speaking, you can always reach out to me after the lecture. You can have the lecture replay. You can have the assignment. And for the replay, you can talk to me. I'll be able to give you the access. All our lectures, you can have a lifetime access for the videos. I'm going to help you set up the access, and you'll be able to see that offline, do some practice. All right, that's pretty much for today's lecture. I hope you guys enjoy the rest of your weekend, and I'll see you guys for the next lecture. All right, bye guys. Have a good one.